Okay, so now I'm going to do a video that will hopefully be the shortest one yet about substructures. So let me share my screen again. There we go. Okay, so we talked about basic algebraic structures. We talked about maps between them. Now we're going to talk about the subobjects. So if you have some sort of algebraic structure, we can think about subsets of that algebraic structure. And maybe I should actually, before I even start the video, let me mention what a subset is. So if I have a set, I can always talk about subsets. A subset S of A, we write this symbol, is another set such that if X is some element of S, then X is also an element of A. So it's another set that's basically contained within A. It contains a subset of the elements of A. That's all a subset is. Okay, so if our algebraic structures are sets imbued with some sort of algebraic operations, and so we can think about subsets, which are also that same type of algebraic structure. And we'll see that subsets that are actually sub whatever type of object come with an injective map that we call the inclusion map. So as sets, if I have a set S that's a subset of A, I get a map of sets, or a function, that goes from S to A, and sometimes I'll write this hook arrow. The hook arrow just means it's an injective map or it's an inclusion. It doesn't mean anything special, really. I'll try to just write a regular arrow. So we get a function I from S to A that's invisible. It takes an x, some element of S, and it maps it to the same element. Because if X is in S, then X is also in A. So it just takes, if here's S, then it includes it into the larger set A. There's A, there's S. So if we have two sets, we always get a function that includes a subset into a bigger set. And we'll want substructures to make this inclusion map a map of whatever algebraic structure. So like we want it to be a group homomorphism or a vector space homomorphism or whatever. So let's do some examples. So subgroups. A subgroup of a group H, and I'm going to denote the operation by plus, is a subset H of G, which is closed under the group operation. So in other words, it's also a group under the same operation as G has. And just to spell that out a little more, a subset H of G is a subgroup if and only if it's closed under both addition. So X plus Y is in H for every X and Y in H. That is, H is closed under the group operation, and it also has to be closed under the inversion. So that means minus Y is in H. If our operation is addition, then I'll write the inverse of Y as minus Y. Minus Y is in H for all Y in H. And we can compactify these two conditions by just demanding that X minus Y is in H for all X, Y in H. That's a condition or a criterion that you can use to determine whether something is a subgroup. And then the inclusion map of sets from H to G becomes a group homomorphism. And it's obvious that it's a group homomorphism because I of X plus Y Well, I is invisible, it just sends this to x plus y. But again, I is invisible, so I of x equals x, and I of y equals y. So this is a group homomorphism. Okay, and then that's actually all we need to check for it to be a group homomorphism, right? So there we go, that's the definition of a subgroup. We have special types of subgroups for groups. They're called normal subgroups. We'll see that we need these later to define quotient structures on groups. But for now, you can just think of them as an extra special type of subgroup. A normal subgroup is a subgroup such that whenever I have n in that subgroup, multiplying it by g on the left and g inverse on the right, leaves you in n. And this is, so if I have an element n, and I take this special multiplication, gn, g inverse, this is called the conjugate of n by g. And the condition is that the conjugates of elements of the normal subgroup by elements of g land back in n. Obviously, if you conjugate by elements of n, you'll land back in n because n is a group, it's a subgroup. But the condition is that it's closed under conjugation by g. So that's the special thing. And we write this special symbol. Okay, so if I have a subgroup, if H is a subgroup of G, I write this notation, less than or equal to G. It's just kind of a fancy subset notation. And if N is a normal subgroup, maybe I should write this to leave open the possibility that it's also equal to G. I'll write triangle less than or equal to. And then when G is abelian, every subgroup is normal, so we don't have to worry about this condition. And in fact, every example of group that I've given you so far has been abelian, because I don't want to talk about any special groups yet. So for now, every subgroup is actually normal. And that's because G n G inverse, if your group is abelian, then Gn G inverse equals G inverse n, because I can commute the elements, but this is just equal to the identity times n, which is just n. And if n is in n, then n is in n. So that's no condition at all if your group is abelian. Let's do some examples. Okay, so like I said, all the examples that I've actually given you have been abelian groups. So I don't want to do a non-abelian example. But let's do this one. So 2z is a normal subgroup of z. And what do I mean by 2z? 2z is the set of even integers, 2n, where n runs through n. Oh, sorry, n runs through z. So it's the set of things of the form, right? -2, 2, -4, 4, -6, 6, etc. And of course, if I multiply this is a group under addition. So if I add two even integers together, if I add 2n plus 2m, I get 2 times n plus m, which is again an even integer. So that shows that 2z is closed under addition. And if I take minus 2n, then it's 2 times minus n. So it's also an even integer. So 2z is a subgroup, and because z is abelian, it's a normal subgroup. And then let me erase all this. Maybe I shouldn't erase this, whatever. You always have two subgroups that are trivially there. One of them is the identity. So the identity is always a subgroup of any group. It's the smallest subgroup that you can ever have. And it's obviously a subgroup because there's nothing to check. And then there's also G itself, which is also always a subgroup. Again, because there's kind of nothing to check. It's definitely closed under multiplication because it was already a group. So those are we call this the identity. We call this the trivial subgroup. And then the biggest subgroup G is just G. If you have a subgroup H that's actually a proper subset, meaning a subset that's not the entire set, we call that a proper subgroup. So a proper subgroup is a subgroup that's a proper subset, meaning it's not the whole set that you started with. Okay, so there's some examples of subgroups. Now I'm going to do a remark, which is that rings are a little bit annoying. So the sub-objects aren't what you would hope that they would be. You would hope everything is just going to be a sub whatever. But it turns out that if you think about sub rings, you don't really get anything good. So we don't really care about sub rings. So I'm going to try to not talk about them very much, but I'm going to explain why we don't care about them. A subring is a subset that's also a ring. That means it's got to be closed under. So this condition here, x minus y is in S, if S is a subring. This says that S, comma plus is a subgroup. Remember that a ring contains an abelian group under addition. And then this other condition is that it should also be closed under the multiplication of the ring. But we'll see that this isn't enough to make the inclusion from S into R be a ring homomorphism. At least not a good ring homomorphism. So I'll illustrate that with an example. So we had that 2z was a subgroup. And it's actually also a subring as well, because I can multiply even integers together and I still get even integers. But remember that Z was a unital ring, meaning it had a multiplicative identity, 1. And 1 was the, 1 was the element that if you multiply anything in Z by 1, you just get itself. 2Z, however, is not unital. So actually, maybe this isn't even the best example. Let me do an even better example. So here, let me finish explaining this. Here, the problem is that the inclusion map from 2Z to Z doesn't send the unit to the unit because there is no unit in 2Z. But it's even worse. Even if I have 2 unital rings, here's an example with 2 unital rings. What about Z cross Z? We haven't shown that Cartesian products are rings, but they are. This is the Cartesian product of sets, things of the form m comma n, n comma n, n comma m, where n is in Z and m is in Z. This is a ring. I can multiply these things together and add them together component-wise. nm plus n prime m prime just equals n plus n prime. Actually, I think we did do this. We did Cartesian products of groups and Cartesian products of rings. Okay, so I won't explain this part. We did it, I think, in a previous video. But I can construct a subring of this by just taking the 0. 0 was the additive identity. So this is 0 is a subgroup of Z, and I can take 0 cross Z. And this is the things of the form 0 comma m. where M is in Z. And both of these are unital rings. The one in Z cross Z, or the multiplicative identity, that's why I'm writing 1, is the pair 1, 1, because if I multiply 1, 1 by m, m, I get m, m. And the one in 0 cross Z is 0, 1. But the inclusion morphism, so this, and then, okay, 0 cross Z is clearly a subset of Z cross Z. And it's a subring because it's closed under multiplication. In fact, it's a ring that's isomorphic to Z, the integers. But the map I from that takes I'm gonna erase here. The map I from 0 cross Z to Z cross Z that takes 0, comma n to 0, comma n, the invisible morphism, is not a unital ring homomorphism. I think I was a little bit wishy-washy about this point in the last video, but a ring homomorphism between unital rings should take the multiplicative identity to the multiplicative identity, because the multiplicative identity is part of the structure of the ring. And this inclusion map doesn't do that, so it's really not a structure preserving map of unital rings. So it's not very good. But then if we require that one, let's say that I just require that all of my subrings, I add an extra condition to a subring that says that the 1 is in S. Well, in that case, all of the subrings just become the whole ring. So it's actually a fact you can prove that if okay, we'll talk about ideals in a minute, but if you're, suffice to say, if your subring contains 1, then it's the whole ring. So I can't take any non-trivial proper subrings of Z, because as soon as I have 0 and 1, I can add 1 to itself a whole bunch of times and get all of Z, and I can take inverses of 1 and get all the negative numbers. So yeah, there's no non-trivial proper subrings of Z if you define subrings to contain 1. So subring is not really the right concept for rings. It's not the right kind of sub-object. So we'll define something else called ideals, which is very similar to the normal subgroups for groups. And if our ring is not commutative, then we have to deal with this business of whether it's a left ideal or right ideal. I'll usually stick to left ideals. So a left ideal is an additive subgroup. So I'm going to keep the first condition that it's an additive subgroup of the ring. But then I'm going to do this thing that's kind of like the normal subgroup condition, but not really. It's that it has to be closed by scalar multiplication on the left by ring elements. So if I take ring elements and multiply them on the left by ideal elements, I land back in the ideal. That's the condition. And we'll see that ideals of rings will allow us to define quotients, and they'll make the inclusion map a ring homomorphism. Okay, so here we go. Let's do some examples of ideals. So now we actually do have real ideals of the integers. In fact, nz is an ideal. We already showed that it was a subring. Well, we showed it for n equals 2, but it's easy for the rest for other n. Why is an ideal? Because n times m, let's say, where m is in z. If I multiply this on the left by an element of the ring, which was z, I'll do lambda. Nah, okay, I'll do r. R times n times m is equal to n times r times m, which is in n times z. Because this is a multiplication of integers and it's an integer. So that's an ideal. We have lots of ideals of z now. And here's another example of an ideal. If you take the polynomial ring, I can take all of the polynomials that have zero constant term. So this is the set of polynomials that start with x, with ax plus a2x squared plus a3x cubed plus dot dot dot. So they're the polynomials with no constant term. We'll call this the ideal generated by x. This is an ideal because if I add two polynomials with no constant term, the result has zero constant term. And if I multiply two polynomials with no constant term, oh yeah, I don't need to do that. If I multiply, right, it's also a subring. But if I multiply a polynomial with a zero constant term by an element of the ring R, then it's a, yeah, then it's still in the ideal. Hang on. Yeah, even if I multiply it by a constant polynomial, the constant term remains zero. So yes, that's true. So this is an ideal. Let's do two more examples: submodules and subalgebras. Oh, I guess it's vector subspaces. Okay, a submodule is a subset that's also a module. And remember that a module has attached to it as data a ring R. So we're talking about R modules. So an R submodule is a subgroup under addition. And then it also has to satisfy that for all ring elements, Rn is in n. And again, notice that if R is not a commutative ring, then this is a left. Maybe I should have included all the words here. This is a left R submodule. And if I want to do a right R submodule, it has to satisfy the same first condition, and the second condition should be changed to n times R is in n for all R in R and n in n. So if you want to multiply your ring elements on the right, you just change everything accordingly. Okay, so that's submodules. There aren't really any special types of submodules like there are for subgroups and ideals. There's normal subgroups and there's ideals. And you can only really take quotients of rings by ideals and of groups by normal subgroups. You can take a quotient of a module by any kind of submodule. There's no really special conditions on it. Notice that this looks very similar to the condition for an ideal. And in fact, remember that if you have a ring R, then it's trivially an R module. And the submodules are exactly the ideals of R. So if you consider R as an R module, then ideals are the same thing as submodules. And then another example is the free module R to the n. Remember that R to the n was just the Cartesian product of n copies of R. And the addition and multiplication, the scalar multiplication and addition were defined component-wise. If I just take 0 in every component, so in other words, this is the submodule 0 cross dot 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 R cross a bunch more zeros. So I only have an R in one component, and in the rest of the components, I just have the 0 submodule. Then I can do component-wise addition and multiplication to this, and I get basically an R submodule of R to the n that's isomorphic to R. It's a ring. Maybe that's not the most interesting example. Then, of course, as always, we have the trivial, right? 0 is the trivial module. And if M is any module, it's a submodule of itself. So those are the trivial cases that we always have. Thought I'd write them one more time. And then when F is a field, when our ring R is a field F, an R module is just a vector space, and we can talk about subspaces. So a subspace W of a vector space V is a subset which is closed under addition and scalar multiplication. Now, since we're working over a field, we don't have to worry about left submodules and right submodules. They're the same. Actually, so I remarked, I think, at some point that vector spaces aren't that interesting. They're characterized by only their dimension. And so vector subspaces similarly aren't that interesting. They're also characterized by their dimension. So if I have a vector space, Rn, which is what all real vector spaces are isomorphic to R to the n for some n. They're Euclidean spaces. The subspaces are just the lower dimensional copies of some Rm, where m is less than n. So maybe I should draw an example of this. What's the only one I can draw is in 2 dimensions. So here's a vector space, R2, the real plane, and it's a vector space. Any line through the origin is a subspace. So this is a subspace. If I take vectors that lie in this line, I'm just adding, addition of vectors just makes them longer on this line, and they stay on this line. And inverses of vectors also lie on this line. They're just the reverse of the vectors that we had. So that's a subspace. Subspaces of R2 are just lines through the origin. And then maybe I will be very daring and attempt to draw R3. So here's a terrible coordinate system for R3. R3 is also a vector space. What do the subspaces look like? Well, I can still take lines through the origin. Those are still subspaces. But now I can also take, let's say, planes that have to contain the origin still. Subspaces have to contain the 0. So I can take planes through the origin. And now I have 2 types of subspaces. I have lines through the origin and planes through the origin. And right, these are basically copies of R. The lines are copies of R, and the planes are copies of R2. So, and I get there's many of these. There's infinitely many subspaces isomorphic to R2, and there's infinitely many subspaces isomorphic to R. But those are the only things they can be. There's no like weird subspaces. They all have to be hyperplanes that contain the origin. That's what vector subspaces look like. And then of course the inclusion of a subspace into the whole space is a linear map. You can check that. Finally, we'll talk about subalgebras briefly. So remember an algebra has 3 operations, and part of the data is the field, or maybe a ring, but I'm going to go with just fields. We're going to have F a field, and A is an F algebra. So A has the operations plus, under which it's an abelian group, and dot, under which A plus dot is a vector space, and then A plus dot cross is an algebra, and A plus cross should be a ring. So an F algebra, A has a subalgebra if S is a subset, which is also an F algebra. and we'll spell out what this means. It means that under the addition, S has to be a subgroup. So that means that if X and Y are elements of my subalgebra, then X minus Y, X minus Y has to be in S for X and Y in S. And then I also have to have lambda S in S for all S in S. So it has to be closed under the scalar multiplication of elements of F. And then if I take two elements and multiply them, I should still land in S. So these two conditions mean it's a subring. And these two conditions mean it's a vector subspace. So it's both a subring and a vector subspace. And I guess it's also an ideal. So there we go. So it's everything. And then the inclusion of a subalgebra into the algebra will be an algebra homomorphism. And let's do some examples. So remember that the complex numbers were a two-dimensional R algebra. You can think of the complex numbers as just a fancy R2, right? As a vector space, it's just R2. And then you put a fancy multiplication on it by considering this axis to be the imaginary axis. And it's an R algebra because it's an R vector space with a fancy multiplication on it. And why is it an R subalgebra? Well, again, it's an R vector space, and then multiplication of real numbers with real numbers. Let me highlight it in red here. There's the real axis inside the complex numbers. Multiplication of real numbers by real numbers gives you real numbers back. So the real axis in the complex plane is a subalgebra. And then here's an example of, being a subalgebra is a pretty strict condition. So many algebras don't have any non-trivial proper subalgebras. For example, the one we talked about where we take R3 and the multiplication on it is the cross product. That gives you no proper non-trivial subalgebras. Why? Because remember that the vector subspaces of R3 are either planes or lines. And if I want it to be closed under multiplication, I have to take two vectors, V and W, in R3, and I want V cross W to be in R3. But V cross W is perpendicular to both V and W. So it spans, like if this is the plane spanned by V and W, let me erase this copy of R. Right, let's say that this is the plane spanned by V and W. I can add these vectors and with each other and get every vector on this plane. But then if I take the cross product of these two vectors, I can get any perpendicular vector. So actually, once you have two perpendicular vectors and their cross product, you have all of R3. So any subalgebra that contains anything other than zero vector automatically already has wait, now I'm doubting myself. Maybe we can have one-dimensional subalgebras. Yeah, okay. Scratch that. I think this is not true. I think it does have it has no two-dimensional subalgebras. Right, as long as I have, but I do have the one-dimensional subspaces. I have the one-dimensional vector subspaces. And those are going to be kind of stupid subalgebras because there's no multiplication. The cross product of a vector with a parallel vector is 0. So, but yeah, I could have one-dimensional vector subspaces, and those will be subalgebras as well, because they're kind of trivially closed under multiplication. But you see that the property of being a subalgebra really restricts the type of subspaces that we can have as subalgebras. Okay, since now I'm starting to say things that are wrong, I'm going to stop here. And that's it.